Okay, it looks like we have about 50 people. Maybe some more will straggle in, but we'll get started. So last class, as I recall, I had another computer failure right near the end of class. I did eventually make it back and finish the lecture a little bit late. It's there on video if you want to take a look. Though I have ordered a new webcam, I'm pretty sure my computer failures are being driven by my dot cam. So we're still using the old dot cam now. I made it through the first class, which means that probably won't make it through this class, but we'll see. But I have a new one being shipped to me, and hopefully that one performs better. The dot cam works fine by itself. And so,
They just said that they're not using the Carolina anymore for cases. They're just going to use the Carolina.
1 second. Yeah, we had a mute issue. Yeah, the Zoom works fine by itself. The dot cam works fine by itself, but the two together seem to cause problems randomly. Anyway, hopefully that'll be resolved next week. And homework 1 was due today at noon. And so hopefully everyone turned that in. If you didn't, don't worry. I dropped one automatically. And there's an extra credit opportunity to drop a second one later on in the semester. So don't panic if you missed it. Often first year students, if they miss their first homework, it's the end of the world, but it really isn't. But anyway, let me show you. We'll come back to the warm-up question in a second. But once you've turned it in, you can go back and look at it still and look at solutions for it as well. So here's the WebAssign page, the front page for students. And you see that homework 1 is no longer one of the options, but you can go to past assignments since we're past the due date and due time. And here we are, and you can see I got nothing out of 10 because I myself forgot to do it, but that's okay, I don't need to. And if I click on lesson 1, so here we are at the homework, and, well, 1 second. I'm in the section 1. Let me go to section 2 because I've already showed it to section 1. I want to make sure you all see the button. So I'm going to switch to section 2, which is your section. Okay. Past assignments. And click on homework 1. I also got 0 out of 10 in your section, so I'm just failing in both of my sections. But anyway, here, right above question 1 is a box, and there's a view key button. Now, once you press this button, WebAssign makes a note that you've seen the key. So if you did not complete the homework due to a valid medical excuse, meaning you have documentation and you're planning on talking to me about it, don't press that button. Because as soon as you press that button, there's no way I can give you an extension. But if that doesn't apply to you, you can go ahead and press the button. Just did. And in addition to seeing what you answered and what the correct answer is, you can now see worked out solutions. And they're pretty brief. And so you can go through them really quickly. For the ones that you got wrong, or even the ones that you got right and you're not sure why you got it right, you can come back and figure it out now. I encourage you to do this before coming to office hours. And if you still don't understand by the time you get to office, if you still don't understand, then please do come to office hours, and I'm happy to work through it with you. And some of them are quite short, some are lengthier with figures, but the idea, these homeworks are supposed to get you ready for the exam. So you'll be coming back here and studying these to get ready for the exam. Okay.
I had a quick question about the homework. So when you select an answer and click submit answer, if it gives you the little check mark, does that mean you got the problem right or that it's successfully submitted?
I think it means you got the problem correct and you got it right. The way we've set it up here is you get 3 attempts, and once you get that the check mark, you mean down here by the answers, right?
Yeah, it's at there's like a green box around the answer choices and a check mark in the bottom right corner.
Yep, I think that means you got it right. Yeah.
All right, thank you.
For the number of submissions, you can come and look at this little plus sign, and it tells you how many times that you've submitted out of your 3. Okay, so that's homework 1. Homework 2, if we come back to the primary page here. It still says it's due next Friday. I'm not going to get through all of lesson 2 by then, so it will likely be delayed as well. How long it will be delayed, I haven't figured out yet, but just keep in mind it's not going to be due next Friday, but sometime after that. And then the next thing on my list is the warm-up question. So let's go back to the warm-up question. I see about 23 of you have responded. Let me explain it and give you a moment to all submit something. So we're looking at a picture here, and this picture is meant to be the western horizon. You are looking west. And I've marked 2 points, A and B. I'm asking, what is point A? And you have a couple options here, and you're supposed to pick 2 of them. Like 3 and 4, sunrise and sunset. Is this a sunrise or a sunset position? And then the other question is this where the sun rises or sets in summer or winter, summer solstice or winter solstice. So pick one of the first 2, pick one of the last 2, and then combine them. So if you pick 1 and 3, you would submit 1, 3, or 1, 4, or 2, 3, or 2, 4. Okay, so I'll give you just a moment. Hopefully we can crank this up to a higher number of responses. Now I should say, if you did watch the video that I assigned, so while you're working on this, I'll just mention, and I mentioned last time at the end of class, though a lot of people were gone because of the technical problem, but going into lesson 2, the first lecture is on archaeoastronomy, Stonehenge archaeoastronomy, and I assigned that lecture by video. So it's to make up for the class that was canceled on Monday. So hopefully a lot of you watched that video. If not, go ahead and watch it. But during that video, I talk a lot about horizon astronomy, where the ancients, like pre-written history, would mark rising points and setting points of the sun and the moon on the horizon. The sun would provide a basic calendar. In the case of Stonehenge, which I spend the whole video talking about, they also explored the moon, which doesn't have calendar purposes, so they're kind of going above and beyond. They're getting interested in astronomy for its own sake. But anyway, this is talking about the sun. Lots of cultures did these kinds of things, either marking them with stones or just remembering where on the horizon the sun would rise and set, first day of summer, first day of winter. If you have a mountain range like in this picture, nooks and crannies could be used as a calendar. And although a lot of this was done before written history, there are some cases like the Hopi Indians in the US Southwest. There's written records of them doing this sort of thing to keep a basic calendar. Okay, so let's see what you got and show the values and show the histogram. And very good. Yeah, you got the right answer. The other class was tied between 1-4 and 2-4, and so I sent them into the breakout rooms and they had to talk it through, but you got the right answer on the first try. So you must be my smart section. And that, damn it, that's recorded now, and I'll post it, and the other section will get offended when they watch it, but oh well. Okay, so let's just review why. First, between 3 and 4, sunrise or sunset. Why is this a sunset? Anyone want to shout it out? What gives it away? It's sunset because it's
on the western horizon.
West, yeah, that's the easy one. Things rise in the east and set in the west, so this has to be sunset. And the question is summer, so if that's west, looking not at, I'm pointing at you, but looking at the screen, if you're looking at west, that means north is to the right and south is to the left. Got that right? Yes, I did. Yep, north is to the right and south is to the left. The pointing is confusing. I don't know if I'm pointing backwards or forward since I'm reversed from the screen, and I'm not going to try to figure it out right now with the video. So in summer, the sun rises north of east, travels a long path over the sky, over the southern sky, and then sets north of west. It's up for a long period of time. In winter, it rises south of east, does a short little hop across the southern sky, and sets south of west. And so this point right here is the sunset, winter solstice sunset. And just to remind you of that, let me throw up a figure here from before. Even if you didn't watch the video, you could answer this. When we talked about this pattern, how it looks from the ground. So again, here's summer. Grab my cursor. The sun is rising north of east. It has this long path, so a long day high in the sky, and sets north of west in summer, and then it's just below the horizon for a short period of time. And in winter, it rises south of east, short hop, sets south of west. So that picture we're looking at goes from here to here, summer solstice sunset, winter solstice sunset, and the equinox sunset is due west. Okay, and again, we talk about this even more in the video because a lot of the ancient pre-written history astronomy was done on the horizon. Where did things rise and set? So I encourage you to watch that video. There's a lot of information in that video, and you're not responsible for all of it. That's intended to be one of our fun lectures. Unfortunately, I can't do it live because we're already a class behind, but watch it and hopefully you'll enjoy it. But just try to take away the basics, mostly having to do with where things rise and set on the horizon. Okay, that was the warm-up question. Last time, I mentioned the weird psychological effect. Before we get into lesson 2, I mentioned the weird psychological effect of how the moon sometimes looks really big and sometimes looks really small. And I said it's not the effect that we described last time, which I'll review, but it's a different effect. It's a psychological effect. And I said I'd explain it, but I ran out of time. So I'll explain to you now because it's kind of fun. Let me pull up the appropriate slide. I think maybe I have it. No, that's for lesson 2. Let's pull it up here. So there is, as we talked about last time, there's a real effect that makes the moon look a little bit bigger or a little bit smaller, and that is the moon's orbit's not perfectly circular. So sometimes the moon's closer and appears bigger. Sometimes it's farther away and appears smaller, just a little bit, a 12% difference. Now, as we also talked about last time, you've noticed, you've looked at the moon before and said, wow, the moon looks really big. Or maybe you looked at it and said, boy, it looks really small. And I asked you, when it looked big, where was it in the sky? And it was on the horizon. I asked you, was it on the horizon? You said, yeah, it was on the horizon when it looked big. And so that is a psychological effect. This change happens very slowly. It takes 2 weeks to go from close to the Earth to farther away, and then 2 weeks to come back. It has nothing to do whether it's high in the sky or low in the sky. This effect that we talked about last time happens very slowly. It's a very small effect. This other effect, it looks big on the horizon. Here's an example of that. The moon looks really big on the horizon and small when it's up in the sky. It's a psychological effect. People normally explain it away in the following fashion, which doesn't really capture the whole story. But when it's on the horizon, you have reference objects. You may see it next to a mountain or a building. You say, oh, the moon looks as big as that mountain. And when it's up in the sky, it's all by itself. There's nothing to compare it to other than the sky itself. Oops, the dot cam. Well, I'm not using it, so it's fine. Other than the sky itself, and of course the moon looks small compared to the whole sky. But that's not the crux of why the moon looks big on the horizon. It's a different effect, and it's an effect having to do with how our brain interprets the sky. Let me switch over to the dot cam. So here's the ground. Let's say we're standing on the ground, and we know the sky is like the celestial sphere. The stars are scattered throughout three-dimensional space, but we can't see distance. So in our mind, all the astronomical objects are the same distance away. The moon, as it's moving across the sky, the same distance away. And so we can draw it like a planetarium dome. Really isn't a celestial sphere out there, but we can think of it that way. And anything out in space is traveling across the sky on the sphere. But our brain doesn't think of the sky as a big dome. Now, maybe intellectually, maybe after sitting through a few lectures you do, but at a gut level, an intuitive level, we envision the sky as a low ceiling. And this is because of clouds. Clouds travel overhead, hugging the ground. And so when they're far away on the horizon, I'll draw one here. Since it's far away, it occupies a very small angle of our field of view. But if you have that same cloud, same size, pretty much overhead or close to overhead, it's taking up a much larger angle. And so we think of the sky in terms of the clouds because that's normally the only thing we really see in the sky. So let me put up a figure that illustrates that. So here's a bunch of clouds. All these clouds are about the same size. I mean, some are bigger, some are smaller, but there's a typical size here. Yet the ones on the horizon look really small, and just because they're really far away. And the ones right here look bigger, and it's because they are literally closer to us. They're not traveling across the sky like this, in which case they would always be the same distance away. They're traveling across like this. And that sets our expectations. We expect things on the horizon to be small and things almost overhead or overhead to be big, because that's what the clouds do. But the moon doesn't do that. The moon actually does travel on that dome. The moon is not traveling on this small ceiling, it's traveling on this dome. So here's a schematic that's a little weird because it draws the moon in front of the clouds, which never happens. The clouds are always in front of the moon. But here you see the cloud when it's on the horizon, far away, it's small. As it's passing overhead, it gets big. But the moon doesn't get big because it's on the celestial sphere. It's not on that low ceiling. So here the moon looks big compared to the cloud. And here it looks small compared to the cloud. And our intuition, our gut, is based on the cloud. If things are on the horizon, they should appear small. The moon doesn't, so the moon looks big to us. And when it's overhead, things should have gotten bigger. The moon should have gotten this big, circle 3, but it didn't. So it appears small compared to our gut's expectation. You follow along? So I'm going to prove it to you. Let's do a few examples here. Now, answer based on your gut. Don't think it through. Just what does your brain initially interpret? So this is a London train station. We have 2 red bars there. Which one's bigger, the one on the left or the one on the right?
The one on
The right, yeah.
Right.
Some people are pointing, but it's reversed for me, so yeah, on the right. Okay, well, let's open this with my favorite program ever made, Microsoft Paint. And maybe I'll shrink it a little bit so we can see the whole thing. And I'm going to grab the bar on the right here, which you all say is bigger. I'm going to slide it over next to this one, and you see it's exactly the same size. So it's a perspective thing. And to tie it to the moon, let me rotate this image. So now this wall is kind of like the sky. The horizon is down here with this poster. When the moon is on the horizon, it appears big. When it's high in our sky, it appears small. But I just showed you red bar is exactly the same size. It's your brain, an optical illusion. Oh, I got an oh wow symbol off of one of the people here. That's great. Okay, let me show you one more, but just keep that in mind. Don't save. And again, there's our moon image, so it's the same deal. And here's another one. 3 vehicles there, and I won't even ask you. I know that the one up here appears much bigger than the one down here. Open with paint. Zoom out a little bit, and I'm gonna grab maybe this one down here at the bottom. Slide it up next to this other car, and you can see it's exactly the same size. Your brain was fooled again. Just how it's programmed, I guess. And I'll rotate this around. I'll put the cars on the top, so it's like the sky again. So think of, instead of a car, it's the moon. I just proved to you it's the same size, but the moon appears a lot bigger when it's low in the sky, appears a lot smaller when it's high in the sky. So there's that effect. Okay, cool. It's not super important or physically meaningful, but it's kind of fun, so I figured I'd start with that today.
I can't believe that got me every single time. That's crazy.
And I explained it first to you, but it still gets you.
Yeah.
Even I look at it and I'm like, oh, the far away car is bigger. But yep, it's just how our brains are programmed. Okay, so that will explain that, because everyone has that experience. They look at the moon and they say, oh wow, see how big it is. Now you know why. Okay, we are moving on to lesson 2. Again, I start lesson 2 with, so lesson 2 is the planets. In lesson 1, we talked about the motion of the Earth, the sun, the moon, the stars, but we avoided the planets because it's a little bit more complicated. So lesson 2 is the planets, and I do it from a historical point of view, which I like. I minored in history just because history classes are like story time. You go there, you sit down, the professor just tells you stories, and I like that. So lesson 2 is story time. I'm going to present the planets from a historical point of view, starting with the ancient Greeks and moving all the way up to physical explanations and Newton. But since I do present it historically, I like to start with archaeoastronomy, which is prehistory, and hence there's that video, a full lecture on Stonehenge. And if you haven't watched it, please do. Again, you're not responsible for all that information, but hopefully you find it as interesting and entertaining as the little thing I just showed you. Okay, but let's move on to the planets from a historical point of view. Get a fresh sheet of paper here. And if we're going to go all the way back to the ancient Greeks, we're talking about the geocentric. So there are two world views here. Geocentric, capital U just means universe. Geocentric model for the universe. So the ancient Greeks put the Earth at the center of all things. They thought that we were that important. And in fact, this is I've mentioned this before. It's a story that plays out throughout the history of astronomy. Initially, they thought Earth was the center of all things. We later learned, no, we're just one of the planets orbiting the sun, but we were convinced the sun is the center of all things. And it wasn't until like 1920 or 30, we realized, no, we're in the outskirts of our galaxy, but we thought our galaxy was the center of all things. And so we keep making this mistake over and over, trying to put ourselves at a special place in the universe. And it begins here with the Greeks putting Earth at the center of all things in the geocentric universe. So we'll start with that, and hopefully we get through it and a little bit into the heliocentric or sun-centered universe today. Let's start with the geocentric universe, and let's start by listing all the objects in the universe. Now, not all the objects we know now, but the classes of objects in the geocentric universe. It's a pretty limited list. So what is the most important object in the geocentric universe? It is the, shout it out.
Earth.
Okay, we're the center of all things. And then what are the next two most important?
Sun.
And sun.
Sun and moon, yeah. Because they're big objects. The sun in particular, it's super bright, but the moon is just as big from an angle point of view, about ½ degree. So those are the next two most important things. What else do we have in the universe, in the geocentric universe?
Stars.
Stars, yep. And I'll list them as fixed stars because they believed the celestial sphere was real. Since we can't see distance, it's easy to think of them as being on a sphere, and that sphere surrounds us. So they thought the sphere was real and the stars were fixed to them. We now know with advanced telescopes and whatnot, we can see stars moving with respect to each other, changing their position slowly with time. But back then, they just thought they were fixed to the sphere. And then what's the other big class of objects that we're going to be focusing on?
The other
Planets.
planets.
Planets, yep. And what are the planets now that they knew of? So what did they consider to be a planet? Go ahead and list them off.
Jupiter.
Jupiter, what else?
Mars,
Mars,
Venus.
Venus,
Venus,
Saturn,
Mercury.
Saturn, Mercury. Yep, you got them all. Not Uranus, not Neptune. It requires the invention of the telescope. You can't see those with the naked eye. And not the Earth. The Earth is not a planet in the geocentric model. The Earth is the center of all things, much more important than a planet. And planet, the word means wanderer. These objects are different from stars. They look like stars to the naked eye. They look like a point, but they're different because they move differently. They wander across the sky, non-uniformly. And we'll get back to that. Well, let's kind of get to it. Well, yeah, let's work our way towards it right now. So I'm going to write this out. It's a sentence, but it's worth putting on the piece of paper. Get my notes a little closer to me. Everything, I'm going to try again. Everything travels east to west over the night. And we know that, we know everything rises in the east, sets in the west. We know it's because Earth is spinning on its axis. The ancient Greeks didn't think we were spinning. We're the center of the universe. We're the center of all things. Why should we move? They thought we were stationary and the whole universe was going around us, moving everything from east to west. But let's focus on the sun and the moon first. But the sun and the moon travel west to east with respect to the fixed stars. So yes, every night and every day, the sun and the moon, they rise in the east, set in the west. They're still going east to west. But if you were to track their position relative to the background stars, they're changing their position. We know this. That's why the constellations change, because the sun is moving to a different part of the sky. And they are traveling west to east with respect to the background stars. The whole thing's going around east-west, but if you were to take a snapshot every day and could see the background stars, which we can't when the sun is out, but if you could, the sun would be moving west to east. And we call this prograde motion. Prograde, kind of normal motion. And let me pull up a figure to help explain it. Okay, so when we were young, we've all played on these before, a merry-go-round on a playground. And so we have one here. Imagine it's one of these merry-go-rounds where the center is stationary. You can stand on the center without rotating and everybody goes around you. So you're standing on the center, watching what's going on. We have horses and things out here in the outer circle, and kids are on them, and the good kids are staying on their horses as they were told. And the whole thing's spinning in a particular direction. And from where you're standing, let's think of this as the east to west motion of the sky. You're standing over here looking up in this direction. The kids are coming up on your eastern horizon and then cycling out of your field of view on your western horizon, east to west motion. Now suppose two very naughty children got off their horses, even though they were told not to, and they start walking in the opposite direction. This one here corresponds to the sun. This one who's closer corresponds to the moon, and they're walking the other way. Now the merry-go-round's going around really fast. They're still being carried across your field of view, east to west. This kid, although he's walking west to east, he'll spin past, coming up in the east, going away in the west, coming up in the east, going away in the west. But what he's doing is traveling west to east with respect to the other kids. If I were to take a snapshot every time this kid got in this position, snap, 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 I'd notice these kids moving the other direction with respect to that kid. And that's what's depicted over here. On the outer shell is the celestial sphere with the fixed stars. And then we have a shell for the sun and a shell for the moon. In the ancient Greek models, they believed these shells were real, transparent. You can't see them, but the stars, the sun, the moon are fixed to these shells. All of these shells are going in the same way, east to west. Just the sun shell and the moon shell are not going as fast, and so they go west to east with respect to the stars. You follow all that? A little tricky, but I think you get it. Okay, good. Let me see what's, let me put up the dot cam and just write down a phrase, and I'll write it down again in a second. But this is called uniform circular motion. The celestial sphere, the sun, the moon, they're on shells that are circles or spheres, and they're moving uniformly. And this formed the basis of all of the geocentric models, and even some of the heliocentric models until we finally got it right. There's this ideal, this aesthetic of uniform circular motion. Okay, before we go to the first model, let me see what slide's next here. Yeah, let's talk about the planets a little bit and why they're different. So this is a diagram showing the motion of Mars in 2009, 2010. So it's starting in the west in September. Here we are in October, so it's doing the west to east motion with respect to those background stars, prograde motion. and then November, and then December, and then January. So you see around December and January, it stopped moving prograde. And now from January to February into March, it's moving back the other direction. We call this retrograde. Pop up the dot cam. So there are three things about the planets that we need to, three things about the planets that we need to explain. The first is retrograde motion. Every now and then, the planets stop their prograde motion, and for a short period of time, they travel backwards, retrograde, east to west with respect to the background stars, and then stops and they go prograde again. Mars would go prograde for like 2 years and then retrograde for a couple months, and then it just cycles over and over again. So why do they go retrograde? That needs to be explained whether it's a geocentric model or a heliocentric model. Let's list all three things, then we'll jump into retrograde. Second thing is brightness variations. The planets vary in brightness. You may have noticed this if you've spent some time staring at the sky. Sometimes they're brighter, sometimes they're fainter. It turns out they're always brightest when they're in retrograde. So these two things are connected. Sorry, I wrote on the dot cam, but you can't see the dot cam. Retrograde motion and brightness variations, they are connected. And that needs to be explained by any model of the planets as well. And the third thing has to do with Mercury and Venus. They're always near the sun. You'll never catch Mercury and Venus on the opposite side of the sky. Mars, Jupiter, Saturn, Uranus, Neptune, they can be 180 degrees apart from the sun, just like the moon during a full moon is 180 degrees away. But Mercury and Venus are always within a certain angle of the sun, sometimes ahead of it, sometimes behind it. So these are three things that need to be explained. So with the geocentric model, let's start with retrograde motion. And I'm going to go to a fresh page here. Put the dot cam back up and then I'll get to that figure. Let's start with the model of Aristotle. The first serious model here for this. Aristotle, he's 384 to 322 BC. So long time ago. And he builds the first model of the universe, and it's based on these aesthetics. I'll write it down again because it's that important. Uniform, circular motion. There are all sorts of ways you could build a model of the universe, but they, the celestial sphere, the sun, the moon, even the shape of the earth, they're all spheres. So they think the idea of a circle or a sphere is fundamental to the universe. So they're going to build their model for the planets out of spheres. And they want the spheres to be rotating uniformly, just like the sun, the moon, the celestial sphere do. But we just saw that the planetary motion is non-uniform. Sometimes it stops and goes backwards. So how do you get non-uniform motion out of uniform circular motion? And the way they do it is they stick two circles together like this. So one circle, there's one circle that goes around the Earth. Nowadays we might call that an orbit, but they call it a deferent. I'm writing it on the dot cam, which you can't see at the moment, but the word is right there on the slide. Then attached to the deferent is a little small circle called an epicycle. I'm going to write that one too. And the planet is attached to the epicycle. So the epicycle, it's a circle. The deferent is a circle. Both of them are rotating at uniform rates. The planet's attached to the epicycle. The center of the epicycle is attached to the deferent and can somehow magically rotate without crashing into the deferent. And the deferent is the center of the deference on Earth. So two uniformly rotating circles connected. And it works qualitatively. We'll see in a second it doesn't really work in terms of if you go out and make precise measurements, but it gets the gist of it correctly. The epicycle is always spinning at a faster angular rate than the deferent. So sometimes these two motions add together and the planet appears to be going not just prograde, but fast prograde. But sometimes There, let me check my time. I go till 3. Oh yeah, we got plenty of time. But sometimes when you're swinging around this way, those arrows cancel out, and even more than cancel out. And the planet will have a net backwards motion, and that's retrograde. Again, I want to emphasize, this is not how the universe really works. This is the ancient Greek perception of it. So as this thing circles around, I think I have a little animation here. There's a blue line connecting the Earth to the planet to the background stars. And you can see as the epicycle circles around, you get that retrograde motion with respect to the background stars. So that's how Aristotle did it. And you get a bonus here. When it's in retrograde, the planet is closest to us. You can see here it's between the deferent and us. And if something's closer, the idea is it's brighter. And when it's farther away, on the other side of the epicycle, being farther away, it's fainter. So in this model, you get it being brighter when you're in retrograde, which is one of the 3 things we have to explain. So we've explained 2 things, retrograde motion and brightness variations. Now, the brightness variations, it's only correct to the human eye. I think I mentioned this a few minutes ago, if back in ancient Greek times we had careful brightness measuring devices, we'd realize that the brightness variations that happen in reality are different from what this model is predicting. But qualitatively, just to define those 2 words, you have qualitatively and quantitatively. And I want you to make sure you know the difference. Qualitatively means generally, descriptively. This works. Quantitatively means measured numerically. And in that case, it doesn't work. If you go and say, okay, I have Aristotle's model, it's predicting these positions on the sky. Does it match up? Not very well, okay? So it's a good qualitative model, but it's not the overall end game. It's kind of inaccurate. Oh, and I should say that this aesthetic, uniform circular motion, that can date all the way back to Aristotle's mentor, Plato. So although he didn't produce a model of the universe, he produced the aesthetics that guided Aristotle. But Aristotle's model is not that great, so what comes next? Next up is Ptolemy, spelled with a silent P. And this is many years later. This is around 140 AD. We don't know his birth and death dates, but he did this work around 140 AD, many centuries later. What he did is he took Aristotle's model and made it more flexible, added more freedom, more parameters to it. So what he did is Earth is still the center of all things, but the deferent is now shifted. And for each planet, it's a different shift, a different amount in a different direction. And also, it's not depicted here, but the epicycle center is no longer on the deferent. It is shifted too. And for each planet, it's a different shift in a different direction. So for each planet, we're adding 2 shifts of magnitudes that Ptolemy can pick and of directions that Ptolemy can pick. He's adding a lot more freedom, a lot more flexibility to the model, which means if you pick those numbers correctly, it's going to do a better job. So let me write those notes on the doc cam. What Ptolemy did is he shifted the centers of both the deferents and the epicycles. The epicycle shift is kind of strange. There's details. It shifted, but then you project it back. You project the planet back to the unshifted epicycle. Don't worry about that. I'm just saying it's actually a little bit more complicated with the epicycles. But all you have to remember is the centers are shifted. And let's look at the whole thing. With this extra freedom, these extra parameters, you have more flexibility and you can make it match the sky better. And so here's the entire Ptolemaic model. And actually, before we dive into this figure, since you have that more freedom, you can, as I have been saying, you get a more accurate description of the planets on the sky. And it's really pretty accurate, so accurate that it was used for 13 centuries. It's not perfect. It does make mistakes now and then. It's a little bit off always. And they knew this back then, but it was really, really good for the time. So good that no one came up with anything better for 13 centuries. And at the beginning of this, it was just an intellectual idea. Some Greeks playing with geometry and numbers, but by the end of this, it had been around so long, it had been adopted by the, many of the world's major religions, at least in that part of the world, as truth, as how the universe worked. And that probably also stretched out these 13 centuries, because by the end, if you were to propose something different, it's blasphemous. You're challenging the teachings of established religions, and they were the centers of power back then. So for those two reasons, it lasted 13 centuries. It was accurate, no one came up with anything better, but then it was adopted as part of the dogma of these religions. And to question it was to question God. So it stuck around for a long time. Now let's take a look at it. So if you look at this, you have the Earth, you have the Moon, the Sun, you have the planets. The planets have epicycles. The Moon and the Earth, their deferents don't have epicycles because they're moving uniformly. The fixed stars, it's not depicted here, but it'd be one more circle. The epicycles are only for the planets to make them speed up and slow down and do retrograde. And if you look carefully at the deferents, they're not concentric. They're kind of shifted a little bit, and those are the shifts of Ptolemy. He shifted them to make the numbers match the sky a little bit better. And this is called a close packing arrangement. You could actually have these deferent epicycle combinations at any distance. Since we don't see distance, it doesn't matter. But the Greeks, they wanted to pack it as close as possible. So you see places where the epicycles just barely graze one another. And this led to a misconception for many, many centuries that the universe is a lot smaller than we later found out that it actually is, because they thought everything was packed in really tight. So you can see the offsets, the shifts, you can see the close packing, and then the final thing that you have to explain is Mercury and Venus always being close to the sun, and they just make this happen by requiring it. So here's the sun, here's Earth. Imagine a line connecting the sun and the Earth. The center of Venus's epicycle and the center of Mercury's epicycle is always on that line. Even as the sun swings around and that line swings around, the center of the Venusian and Mercurian, I think is the word, epicycles, they're always on that line. Not for any good physical reason. Nothing in this model has any good physical reason. Just they demand it to be so. And when you do that, it means the epicycles will always be between Earth and the sun. So Venus is always going to be within this angle of the sun. It can never be on the other side. And Mercury will always be within the smaller angle of the sun. So that's how they get their third requirement. We have explained using the deferents and the epicycles. We've explained the retrograde motion. Also explained the brightness variations, because it's closer to the Earth when in retrograde. So these two things go together, check, check. And then Mercury and Venus are always near the sun just because they make it that way. It's by design. Now, it's very accurate. But a modern day scientist would look at this and laugh, because it's accurate because it has so many things you can adjust, so many buttons and knobs and levers, so many parameters. There are over 200 numbers that describe this model. And if you have a model that has that many parameters, you can kind of make it do anything you want it. Ever hear of Occam's razor? If you have a phenomena and you have two different explanations for it, the simpler one is usually correct. And what we're looking at here is not a simple explanation. It has like 200 and some things you have to adjust to make it work. And let me just play a little video to demonstrate this. I have to slide you out of the way, get to my lesson 2 slides. And okay, so this is a single planet. Make it bigger and get past the words. It's a single planet on 100 epicycles. It doesn't represent anything in physical reality. It's just to show that you know, with 100 epicycles, I probably have 200-300 parameters here. With 200 or 300 parameters, I can explain any motion I want. And you can see how complicated the motion of this planet is. I'm going to skip ahead a little bit. That's too far. Okay, and it's going to start tracing. And this is what we call a closed orbit. It actually repeats and traces the same thing out time and time again. And shout out once you figured out what it is.
Is someone drawing something?
No, he's not drawing something, but it's someone.
Is it like Neil deGrasse Tyson or something?
It's not Neil deGrasse Tyson.
Someone sleeping?
deGrasse Tyson is offended.
Bart Simpson.
Oh my god, it's Homer.
Homer.
That's Homer Simpson. Okay, and then it goes on and repeats itself. Again, the point is, with this much complexity, I can do anything. I can draw Homer Simpson. And so, just because I can explain the motions of the planets doesn't mean this is the right explanation. A modern day astronomer would want a simpler explanation. So I still have about 4 or 5 minutes. So I'm gonna push on. Let's summarize the geocentric model and transition into the heliocentric model. I have some videos here that can help with this. So this is a little animation of about a year and a half, about 500 days of the geocentric model, Earth at the center, everything traveling on its deferents and the planets also on its epicycles, giving you those little loop-de-loops, which are the times of retrograde motion. It's a very complicated motion, but underneath it's built up from uniform circular motion, which is what the ancient Greeks wanted. Now this video is actually missing one aspect. In reality, you know, these are just the motions with respect to the background stars. In reality, the whole thing is spinning once a day, and this is 500 days. So imagine taking this, this window and spinning the whole window 500 times as it's playing. That is the real geocentric model. That we take out that daily motion just so we can see it. It'd be a big blur, and we wouldn't be able to focus on things. But it's there, don't forget about it. Now I'm going to show you the equivalent video for the heliocentric model. So here, there we go. Much simpler looking. We have the sun at the center. The planets are just going around on circles, or as we'll learn once we get to Kepler, ellipses that are close to circles. And in this case, the Earth is one of the planets. So this represents a big downgrade in our place in the grand scheme of things. We're now just one of the planets orbiting the sun. Also, in the heliocentric universe, Earth spins on its axis. The whole universe doesn't spin for our personal benefit. We just spin as one small member of the universe. And that seems nice and simple, but we still have to explain these same 3 things. We have to explain retrograde motion. We have to explain brightness variations, and we have to explain why Mercury and Venus are always close to the sun. We'll tackle those next time, but let me, before we go, I just want to set up the first person to propose the heliocentric model. Come back to this slide in just a second. That'll be my second to last slide for the day. So on the dot cam, I'm switching over to the heliocentric universe, and I may go 1 or 2 minutes over, so bear with me there. Heliocentric universe, and again, we have to explain these same 3 things, and it begins with Aristarchus. I guess that should have been a capital A. It's a name. He lived 310 to 230 BC. So a long time ago, came after Aristotle. So Aristotle went first, presented his model of the universe. Aristotle was a popular guy, everyone liked it. Then Aristarchus came up and said, no, I believe the sun's at the center, and presented the basic modern day heliocentric model all the way back then. Sun at the center, Earth merely a planet, just like the others, all going around the sun, Earth spinning on its axis, the moon going around the Earth. That's the basic model. But everyone got hung up on Earth spinning on its axis. If Earth is spinning on its axis, why don't we feel it? Like if you're on playground equipment, a merry-go-round, you feel it spinning. If you're in a car and you take a turn too quickly, you feel it, you're thrown to the outside. If we're standing on a rotating planet, why don't we feel it? The sky rotates east to west. It means the planet's rotating west to east. And so if the planet's rotating this way underneath us, we would be thrown backwards. We should feel a force pushing us to the west constantly. Why don't we? Well, Aristarchus could not answer that question. It takes Newtonian physics developed a long, long time after this to answer that question. Once you have Newtonian physics, you can calculate the strength of that force. We call it the Coriolis force. And it's really small compared to the force of gravity. The force pulling us downward is so much stronger than the weak little Coriolis force that we don't even realize it's there. But that's the answer, but Aristarchus couldn't give it, so nobody listened, and the heliocentric model died all the way until 1400s, 1500s. Actually, till 1543 is when it reemerged with Copernicus. I just want to show you two slides, and then I'll call it a day, demonstrating to you that the Earth is indeed rotating and what this Coriolis force is. So in this example, imagine launching an intercontinental ballistic missile from the North Pole down to some target here in the ocean, in the Atlantic Ocean. If we live in a geocentric worldview where Earth is not rotating, well, once that missile's launched, it's separate from the Earth. It's going to travel on its course, no matter what Earth does. And if Earth is stationary, we hit the target. But if we live in a heliocentric worldview, once we release that missile and it's traveling, Earth is rotating underneath it. And by the time the missile gets down here, some part of South America just orbited or just rotated into position. We just bombed, I don't know, Colombia by mistake. So before you go launching missiles, you better know if the Earth is rotating or not. Now, from the viewpoint of someone down there in South America watching this, first they see the missile and it's heading off to the left there, going to go in the ocean, but then it changes its path. It's being pushed to the west. It's not really being pushed. We're rotating underneath it. This is what we call a fictitious force. But from our point of view, it looks like things are being pushed to the west. Just like I said, there should be a force that we feel pushing us to the west. And you see it a lot with air systems. Air, the atmosphere circulates north to south, but it's being pushed west, and that's what creates these hurricanes and cyclones and things like that. Last slide here. You've seen this before in museums. Have you ever seen the giant pendulum? Go to one of the bigger, more famous museums, they have the giant pendulum. This is the same thing. It works on the Coriolis force, and it's proof that the Earth is rotating. And the best way to understand it is imagine this at the North Pole. Right on top of the planet, we have a long pendulum attached to the roof. Let's say it's kind of friction-free. It can rotate without much friction. You send it swinging back and forth, and it's just going to keep swinging back and forth. Earth spins underneath it. And so from our point of view, the angle will change. It starts swinging like this, but over the course of the day, it changes its angle. Sometimes they put pegs here, and it will knock over like one peg every hour. And it looks like it's changing its angle in which it's swinging, but really Earth is spinning underneath it. And this is a Foucault pendulum. I think it dates to like the 1700s. So it took a long time to prove that Earth is rotating, but that's proving a major part of the heliocentric worldview. For the other three major things, retrograde motion, brightness variation, Mercury, Venus, we'll tackle that next time. Okay, I'll stop there. Thanks a lot, and I'll stick around for questions.
Thanks.
Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.
Any questions? Going once?
Oh, real quick, sorry, I'm trying to like get like my life in control. But like for the assignments that you want to do on the web assign, it's the you want us to look at the moon, correct? Then you
Yeah.
want. Wait, can you just go through those real quick so I can like write them down?
Absolutely. So let me pull up WebAssign. And I'm going to go to the ebook. So there are 3 of these observing exercises. The first is under motion of the celestial sphere. And it's described down here. You basically go out, you draw the northern sky and the southern sky early in the evening. You come back many hours later, draw it again, include some reference points like buildings, trees, but draw both times from the same position, and notice how the stars move. So you're going to draw some stars, you can connect the dots, make your own constellations, and notice the motion of the sky and how it's different in the northern sky versus the southern. That's exercise 1. Then I had one where, let's see, this is under seasons. There's a description and also a worksheet. And you're going to go out maybe about once a week throughout the whole semester, measure how high the sun is in the sky around midday. Just eyeball it without looking directly at the sun. Block the sun with your hand, and the angle you hold your hand, if this is 0, this is 90, 45, 30, 60. You can just kind of approximate how high is the sun in the sky at midday. And also you need to approximate the length of day. And you can do that by just seeing when the sun sets, or you can just look it up on your phone, how long is the day. But if you want to do it old school, you figure out when did the sun set, and you essentially double that time.
Okay.
If it's daylight savings time, you have to subtract an hour and then double. You do this about once a week, and the goal is for you to notice the sun is getting lower and lower in the sky every day, and the days are getting shorter. And then the last exercise was with the moon. That's under lunar month. Nope. It's under lunar phases. Here you go. And it's another worksheet. It's best to start this on a new moon. So you're going to have to wait about 2.5 weeks to do this one again. But on the day of the new moon, or the day right after the new moon, go and write down the date and describe the phase, sketch it, and measure how far is the moon from the sun in the sky. If it's right next to it, that's 0 degrees. If it's over here, maybe that's 10 degrees. This is 90. If the moon's coming up when the sun's going down, that's 180 degrees. And I want you to realize the relationships between phase and how close the moon is to the sun in the sky. And there's a figure I put up to demonstrate this, and I'll just pull it up one more time. And for this, you always make this measurement at sunset. So the sun will always be in the west, and you're measuring the phase of the moon for each of these days over the course of 2 weeks, and how the phase changes as the separation between them increases.
All right. Thank you. I appreciate that.
Sure, my pleasure.
Have a good one.
You too.